Hello students, in this video we'll prove a formula for the Gaussian curvature times the surface area differential. So what we're going to do is we're going to consider the differential K d sigma, where here K is the Gaussian curvature. Okay, we're going to see that this quantity comes up in the Gauss-Bonnet theorem. So this expression, this differential, arises in Gauss-Bonnet. And so I want to figure out ways of expressing this differential in a more elementary fashion, okay? And so to do this, what we're going to do is the following. So a proposition can be very useful for us. It says, given a surface and a choice of an orthonormal basis for the tangent space, TPS, at every point. At every point P. Okay, it's essential that I need every point P over here. And so what I'm going to do is this. I'm going to say it like this. It's going to be F hat G hat, like that. That's my basis. Okay? Excellent. And oriented in such a way, such that what? Such that F hat cross G hat is N hat, okay? Then what we're going to do is we're going to consider then F U G V minus F V G U can be written as K, the scalar curvature, times the square root of EG minus F squared, right? Which exactly is what? Which exactly is just K d sigma for the surface area element, right? Okay? Excellent. With a dA, of course, right? So K dA. That's our surface area differential, okay? And I really need to put like a dA over here to make sure that they're both differentials, okay? Excellent. This implies this is equal to that. Let's do it like this, actually. So this is equal to this, and this implies that K d sigma is equal to what? That K d sigma is equal to K dA, like so. Beautiful. Okay? So in other words, this expression over here, this determinant-looking expression, is the expression that we're going to see when we're evaluating these types of integrals. Okay, excellent. So how do we do this? Well, we know that f sub u, the derivative of f sub u, so here's a proof, f hat u, can be written in terms of g and n, right? Because fu is perpendicular to f, right? So I can write this as some number alpha g hat plus some number lambda u n hat. And then then f sub v, or well, I guess we can do the other one too. So f sub v is also going to be perpendicular to f. So this is going to be some number beta g hat plus lambda sub v n hat. Okay, good. In other words, I can represent the derivatives of this f vector in terms of the g, because that's in the tangent space, and then also in terms of n, right? And of course, since g dot fu is equal to negative fu dot g, I can also conclude this. I can also write this that g u hat is going to be, since if I dot product this with g, I'm going to get fu dot g is alpha, but I know that f dot gu is the same, so this is going to be negative alpha f hat. That just follows from the orthogonality of these two things, plus sigma u n hat, some other coefficient, and then g hat v is going to be negative beta f hat plus sigma v n hat. Beautiful. These, of course, are dot products, right? Okay, excellent. So now we can write our conclusion from this. So what is fu.gv? Well, g.f is going to be 0, g.n is going to be 0, and then so those terms are 0. So n.f is going to be 0, and then this dot is going to be 1. So it's going to be this is going to be what? So in other words, we have fu hat dot gv hat minus what? Minus fv hat gu hat is exactly going to be what? It's going to be lambda u sigma v minus lambda v sigma u. So that determinant looking expression. Excellent, okay? All right, and so now let's recall that if I look at nu cross nv, the derivatives of the normal vector with respect to u and v, this is equal to k, and then what? And then ru cross rv, right? Excellent. Now, of course, what is k? K is going to be ln minus m squared over what? This expression over here is the normal vector up to the factor of eg minus f squared, right? So this is just going to be an eg minus f squared for the Gaussian curvature. And then this thing is going to be what? Then this thing is going to be square root of eg minus f squared n hat, okay? So in other words, we just have the following relationship. We have that, if I look at nu cross nv, that is equal to what? That is equal to ln minus m squared over what? Over the square root of eg minus f squared n hat. And so in other words, this expression over here, this ln minus m squared over this eg minus f squared is exactly what? And so this implies that ln minus m squared over the square root of eg minus f squared is nu cross nv dot product with n hat. But I know what n hat is, right? N hat by assumption is what? N hat by assumption is f hat cross g hat, right? So now we're almost there. So now what's my conclusion? So what can we do? So now I need to do n. So these things, I'm going to dot those with what? With f cross v. So now nu cross nv dot n is the same thing as what? Is the same thing as nu cross nv and then dot f cross g. And now I can use Lagrange's identity, by Lagrange identity. By the Lagrange identity, this is going to be what? This is going to be equal to nu dot f nv dot g and then minus nu dot g and then what? Then nv dot f. But I know that n dot f and n dot g are equal to 0, so I can pass the derivative from the n term to the g term with a negative sign. So I can pass one derivative over here and one derivative over here to get two negative sign penalties, so the sign's preserved. Likewise over here, I can pass this derivative over here with one negative sign, this derivative over here with another negative sign, so all the signs are preserved. So this is nothing more than just n dot f hat of u, n dot gv minus n dot gu, n dot fv. Like that. Beautiful. Now what is n dot fu? N dot fu is lambda u, so this is lambda u. That is sigma v minus, that's going to be a sigma u lambda v. And what is that? That's exactly just fu dot gv minus fu dot gu. So this is equal to fu dot gv minus fv dot gu, like that. Okay, so let's run this all back and see what we got over here. So in other words, this expression over here, this expression, it looks like this, looks like Lm, just the Gaussian curvature, times root EG minus F squared, the Gaussian curvature times this thing over here, is exactly equal to what? Is exactly equal to this expression over here. That is what? That is fu.gv minus fe.gu, and so that proves this result over here. So when we encounter surface area integrals that involve the Gaussian curvature, they'll going to be Gaussian curvature times this surface area factor times the ordinary xy or ordinary area element with respect to the parameter space, right? So in other words, if you want to move from k sigma to the ordinary differentials with this expression for fu.gv minus fv.gu for a choice of orthonormal basis of the tangent space at any point will play an essential role in the proof of the Gauss-Bonnet theorem. Thank you very much.